Hello everyone. Okay, so this is part 2 of our introduction to physics in grade 9 and grade 10. And we left off at this particular slide and we were looking at the difference between precision and accuracy. And so you should have your answers for the 4 different dartboards right now, and those are so the first one is high accuracy and high precision. And that's because well, when we're looking at precision, what we're looking for is, are all the points close together, right? And the reason why is because if you're able to consistently get every single value as close to as close to your intended one as possible, that means you're highly precise. And in order to be accurate, however, it has to be as close as possible to the actual correct value, the right value, which is the closest to, whether it's the natural real life value, essentially. So that's why this is highly accurate and highly precise. If you look at this one, well, all the points are together, right? And they're close together, which means they're precise, but they're not accurate because you're trying to hit the middle of the dartboard. So you're consistently missing your shots. Over here, you can see the person is highly accurate because it's always around the bullseye, but it's not very precise because it keeps landing here and there and here and there. So it's highly accurate, but not very precise. And this is what you really don't want in general. So it's not very accurate and it's not very precise because it's just all over the place. And that brings us to SI units, which is the International System of Units. SI is swapped around because it's in French originally. And these are basically the fundamental units that you need to know. And obviously you'll be familiar with the first 3, of course: length, mass, and time, meter, kilogram, and second. Of course, there are imperial measurements as well, which are inches and pounds and, well, seconds. But in science, we obviously use metric system. Then we have 4 other units, which you also do need to know, because they will be covered later on during the course, as well as when you go on further in high school. And those are electric current, which is measured in amperes. We have thermodynamic temperature, and you might have expected this to be degrees Celsius, but we actually prefer to use Kelvin in physics because Celsius is kind of tricky because it uses negative degrees, which is not really. There's no such thing as negative temperature. So we'll get into that later on when we do thermal physics. But basically, the correct scientific unit for measuring temperature is Kelvin. And then we go to luminous intensity, which is a candela. And this one you don't really need to know yet because it's not in the MYP syllabus. But it's useful to know just for general knowledge and just to make sure the table is completely put it in here. So it's good to know. And amount of substance, you do need to know that as well, and that's the mole. And it's just a number which we use for measuring large quantities, which we will cover later as well. So derived units. And now these are basically the fundamental derived units. And these ones you absolutely need to know as well. So speed is distance traveled in a given amount of time, so meters per second. Sometimes it'll also be written as change in meters per second, so change in distance traveled. That's also valid. Then we have acceleration, which is the change in speed in a given amount of time, and this is measured as meters per second, which is why it becomes meters per second squared, as you can see over here. This up arrow means squared. And a lot of times exams will try to trick you by saying meters per second, and that can be confusing, but it means the same thing. Meters per second is the same thing as meters per second squared, right? So that's acceleration. And it can be positive or negative. Negative just means it's in the opposite direction. And then area, volume, you should know. Density is mass over volume. Now, you would measure this in kilograms per meter cubed. This is just an example of how this can be measured, but really when we do calculations in physics, we always want to use SI units, which means we always use the same units over here. We don't use centimeters, we don't use grams. We'll always use meters and kilograms specifically as much as possible, just because that makes calculations a whole lot more easier for everyone else, for everyone involved. So kilograms per meter cubed. Sometimes the question will give you grams per centimeter cubed and then ask you to convert. So, be mindful of that. And we have frequencies, which is number of occurrences in a unit in a given amount of time. So this is measured in hertz. And so basically, this is how often something happens. Again, it's something which we'll get into later, and it has a specific equation which we'll also get into later. But that's also something you should know if you like to plan ahead. So dealing with magnitudes of scale. In the world of physics, we often deal with numbers that are very big and very small. So to make life easier, we use standard form or scientific notation when we're expressing these numbers. So when we write standard form, we want to make sure the number on the left is between 1 and 10 always, okay? And basically what we do is we take a number which is between 1 and 10, and then we multiply it by 10 to the power of p, and where the p can be any integer, right? And the whole idea of this is basically, if we have the number, let's say 6 trillion, right? I could write 6, 0, 0, 0, and just write an endless amount of zeros. But then that's a lot longer than but then if we want to shorten that, we can just write 6 times 10 to the power 8 or 9, right? Whatever that number is. So if we just write the number like this, it saves us a lot of time. It's a lot shorter, and it's also a lot easier to do calculations when you're dealing with big numbers, and we'll get to that later. So that's why whenever we write a number in standard form, the number on the left must be between 1 and 10, because if it's not, then it defeats the purpose of standard form. And we normally write in standard form to 2 decimal places. Now this is not necessary. It might not. The question might ask you to write to 1 or 3 or 4 or no decimal places at all. So that definitely should take more importance. But if it's not specified, general rule of thumb, it's a good idea to write it to 2 decimal places. That's generally a safe bet. And so one thing to remember is that the powers of 10 defines the order of magnitude, which increases very fast, obviously. So it increases in tens. So you have to remember that the difference between 10 to the power 4 and 10 to the power 2 might not sound like much because it's only 2 and then 4. But it's actually 10 to the power 4 is 100 times bigger than 10 squared, right? Because you're multiplying it by 10 squared, which is 10, which is 100. So every single integer increase will increase the entire number by 10. And so that's why it's very important to understand just the sheer scale that we're talking about. And so here are the prefixes which we use. Ignore this. This is incorrect. I mean, relative to this, I just noticed that. So ignore that. But if you look at these numbers over here, they give you basically prefixes that we use to describe, let's say, 10, 100, 1000. So all of you should be familiar with kilogram, for example. So a kilogram is 1000 grams, right? As you can see here, 1000 kilo, and you multiply it by 1000. If you know your computers well, you'll know about gigabyte and megabyte, and so those are also prefixes which we add. So megabyte means 1 million bytes, and gigabyte means 1 billion bytes, and so that goes the other way. Centimeter is 1/100th of a meter, millimeter is 1000, and so we go all the way down. It's very useful to know this. You may not necessarily need to know this in NYP, and you might not have to memorize this, but it just saves you a lot of time if you know it, right? Because if you keep having to scramble through them, through your formula booklet every time you see deca or hectometer, then it's obviously gonna get very tiring and it's gonna waste a lot of time. So try and memorize the important ones like millimeter, centimeter, decimeter, as well as kilo, and that should be good. And then if you can, try and figure out the ones afterwards as well. Then order of magnitudes. Now this is here just so that you can have a read through all of it, and basically it gives you kind of a scale, right, of how order of magnitude varies and how the scaling works. So as you can see, we have 10 to the power minus 27, which is extremely small. And then we have a proton, which is 1,000 times bigger, and it's 10 to the power minus 24. And then we have a virus, and then it keeps gradually climbing up. The difference between an ant and a human being is only 5 if you look at the power symbols. But that 5 means that there's a difference of 10 to the power 5, which means a difference of 100,000, right? So that's still a very big difference. And so you got to remember that the power symbol means that it's increasing in tens. You're not just multiplying it by 5, you're multiplying it by 10 to the power 5, which is 100,000. And that brings us to scalar and vector quantities. In a nutshell, a scalar quantity measures only the magnitude or quantity. It's how much of a substance there is. So you'll have one piece of information to tell you, how much of it there is, but you won't have any second piece of information to tell you the direction or anything else about that unit, right? So examples are speed, distance, mass, volume, temperature, or energy. So you'll only be given one value, which will tell you how much there is, but you won't be given any other piece of information. So Victor walked 3 miles around the park at 2 miles per hour. So there's 2 scalar quantities in this. Can you guess which ones they are? Yeah, so there's speed, which is 3 miles around the park. Now the reason why that's not a vector is because, for all we know, Victor could have traveled in circles the whole time and just come back to the same starting point. But we're not concerned about that. We're just concerned about how many steps he did, right? And so because of that, 3 miles around the park is just his distance. That's a scalar quantity. And then at 2 miles per hour, we're not concerned about which direction. Was it clockwise? Was it anti-clockwise? We're not concerned with that. And so this just becomes a scalar quantity for speed. A vector, on the other hand, implies quantity as well as direction. So velocity, displacement, acceleration, forces, those are all examples of vector quantities. So the car traveled 25 meters per second east. That is a vector quantity because, well, first we're identifying the scalar portion of it, which is 25 meters per second. That's the same as speed. But then we're adding another piece of information, and that's east, right? So we're giving him a direction. He's traveling eastwards. So now we know that there's 2 pieces of information, therefore it must be a vector quantity, right? And often when you have an exam question, a vector will always be given in a diagram, with an arrow pointing in the direction. If it's like, let's say, forces or acceleration or any of these, basically, you'll often have an arrow, not always, but often. So if you see an arrow, that's a good indication that it might be a vector quantity. And so that brings us on to graphs, which we will explore in the next video.